Today we're going to look at an RC circuit, which is a circuit that has a resistor in combination with capacitors. I made this circuit a little bit more complicated in that it has two capacitors in parallel with another capacitor that is in series with those two, just so we can handle some of the math that you need to deal with when you deal with an RC circuit. You'll see that it's very simple to deal with. Alright, the first step we need to do is to minimize the parallel portion of the circuit that has the two capacitors. And capacitors in parallel usually just add up in this way. So to get the total capacitance of those two capacitors, you just have capacitor 1 plus the capacitance of the second one. So let's get those two values. The first one is 2 microfarads and the second one is 3 microfarads. I kept the math simple just so you can see. And so here we go. We have 2 microfarads plus 3 microfarads. So that gives me a total capacitance of 5 microfarads. Okay, so this portion of the circuit right here, these two capacitors in parallel is the same as the value of a 5 microfarad capacitor. So that's the first step to handle this circuit, is to minimize the parallel capacitors into just one value. Okay, so now that we have simplified the two parallel capacitors into one value, you can redraw this circuit to represent that result. So I'm going to redraw this real quick, because now that I have my 5 capacitor value, alright, so now I know that the 2 microfarad and the 3 microfarad capacitor, they got combined into a 5 microfarad capacitor. So now you see what I have left in the circuit. All these three items are in series. The 5 ohm resistor, the 5 microfarad capacitor, and the other 5 microfarad capacitor. The next step is to combine the next two capacitors. But these two capacitors are now in series, they're not in parallel. And there's 3 methods by which we add those. And I'm going to show you all 3 methods. And you'll see that we get the same value. It doesn't matter what method you use. It's pretty much up to you what you want. The equal value method you can use when the two capacitors you're looking at have the same capacitance value. Since I made the math simple, these two capacitors have the same capacitance value, I can use the same value method to add them. And basically what that method is you get the value of the capacitor, which is 5 microfarads for both, and you divide it by the number of capacitors that you have. I only have 2 of them. Well, this is really simple. So 5 divided by 2 gives me 2.5 microfarads. So this is the equal value method. Because the two capacitors have the same value, 5 microfarads. This one was microfarads 5 and this one was 5. I can use the equal value formula to get my value for the overall. Okay? The other method by which you can get the total value is the product over sum. And the product over sum looks like this. The total capacitance is the product of the two capacitors, 5 times 5, divided by their sum. 5 plus 5 is 10 microfarads. And now you just divide and do your math. 5 times 5 is 25. Divided by 10, and that gives me 2.5 microfarads. So as you can see, I get the same value, even though I use 2 different methods. So this is my total capacitance, my total capacitance. The third method by which you can get your total capacitance when you have in-series capacitors is the reciprocal method. And the reciprocal method, just for ease of use, I'm going to write it like this. You get the value of the first capacitor, the reciprocal of that, plus the reciprocal of the second capacitor. Remember that they both had the same value, 5 and 5. And all of that sum, you take the reciprocal of. I wrote it this way because it's very simple to handle with your calculator. On your calculator, you have the reciprocal button, so you just punch these numbers exactly how I wrote them. So if I do that, if I do 5 reciprocal, so 5 reciprocal button, plus 5 reciprocal again, and press equal, that gives me a value, and then I just push the reciprocal button of that, and that gives me my answer, which is 2.5 microfarads. So as you can see, it doesn't matter which method you use to get your total capacitance, you get the same value. 2.5, 2.5, 2.5. It just depends on what the circuit looks like, okay? So now we know that these two capacitors combine into one simple capacitor, and I'm just going to redraw the circuit. Now we know that the total capacitance after all of that is 2.5 microfarads. Alright, so now that we have pretty much minimized all the capacitors that we had in the circuit into one capacitance value, okay? Remember that we spoke previously, because this is in microfarads and this is in ohms, you cannot add these. You cannot do any math with these right now. You have to change this microfarad value into an ohmic value. In order to do that, you need to change the capacitance into capacitance reactance. Now, the formula to get the capacitance reactance looks like this. You get the capacitance reactance equals to 1 over the multiplication of 2 pi times the frequency times the capacitance that you have for the circuit. Another way to write this formula is this way. I like to write it this way because it tells me what to do with my calculator and I get my answer like that. But it doesn't matter which one you use, it's your preference. Alright, so let's replace some values for this. We have the capacitance is equal to 1 over 2 times pi times the frequency of the circuit. So let's get that. The frequency of the circuit is 60 hertz. Times the capacitance. The capacitance that we found, if you remember, was 2.5 microfarads. So this value goes in for the capacitance. 2.5 microfarads. Now, one key issue here. You notice that I put the 2.5 microfarads, but in this formula does not allow you to have the numbers in the microfarad form. You have to put them in just straight farads. So you need to know how to change this number into a farad value. The way I do it is change this 2.5 and just add 2.5 times 10 to the negative 6 farads. Because a microfarad is 10 to the negative 6 of farad. And this allows me to change this number into this number so I can work with this formula. Okay? I'm going to do the same thing over here just so you can see. It's going to be 2 pi times the 60 hertz times my 2.5 times 10 to the negative 6 farads. So now all I got to do is put all these fancy numbers in my calculator. So the 2 pi times the 60 hertz times the 2.5 times 10 to the negative 6, and I get my value of 0.000942 ohms. So this is the entire capacitance reactance for that circuit, for the for the capacitors. So now this capacitance, I have changed it to an ohmic value, which is 0.000942 ohms. Now that I have an ohmic value, I can combine these two ohmic values. So now that we have the capacitance reactance for the capacitors, which is the ohmic value, now I can combine the ohmic value of the resistor with the ohmic value of the capacitors. But remember what I told you before, that because this is a resistor and this is not a resistor but a capacitor, you cannot just add these two values linearly. You don't do 5 plus 0.042. You have to add them in this way. And the result that you get is called impedance. It's just because you have a capacitor involved, and that's what it's called. But it's still an ohmic value of resistance for the entire circuit. So let's go ahead and let's replace these with the values that we have. The resistor value for this circuit is 5 ohms, and the reactance capacitance is 0.00942 ohms. I want to get these two values and replace them into this formula. So let's do that. So I have the impedance is equal to the square root of the resistor value squared plus the capacitance reactance value squared. And all of that square rooted. So you get your handy dandy calculator and you do the square root of 5 squared plus 0.00942 squared equal. And of course, because this value is so small, I get a result of 5 ohms. So this is now my impedance. It's the total resistance for this circuit. Now I know that the total resistance for the circuit, which is called impedance, is 5 ohms. That is the total resistance in this circuit. Now that I have the total resistance, I can calculate other things. Okay, so now that I've calculated the total impedance for the circuit, of course we can get the total current in the circuit. And as you can recall from Ohm's law, if you want the total current in the circuit, you need the total voltage, and you divide that number by the impedance you obtain. So let's get some values. I need the total voltage and I need the impedance. So I go back to my circuit and I see that the total voltage is 120 volts and we have 5 ohms for the impedance. So I'm going to substitute these two values into this formula. So let's do that. I have the total current is equal to my total voltage, which is 120 volts, divided by the impedance I calculated, which was 5 ohms. So now all I do is get my calculator and do 120 divided by 5, and I get 24 amps. This is the total current that flows through the circuit. So I can substitute this value. Total current is equal to 24 amps. Alright, so just to review, we have changed the microfarad capacitance into capacitance reactance, which gave me the ohmic value. We combined the ohms value for the capacitors and the ohmic value for the resistors to give me my total impedance. And we used the impedance value to get my total current. Now that I have the total current, I can calculate the power triangle for this circuit. So this is very important for you to remember. The true power always comes from the resistor. The apparent power is the total power of the circuit, so you need the impedance. And the reactive power is the power that comes from the capacitors, so you need the capacitance reactance to calculate that. So I'm just going to substitute values here for these numbers and see what we get. For the power of the total circuit is, remember that the current is 24 squared times the impedance, which we calculated to be 5 ohms. So now you just get your handy dandy calculator and you do 24 squared times 5, and that gives me 2,880 watts. This is the apparent power. Now we're going to calculate the true power. So the true power, remember, comes from the resistor. So the power is, once again, 24 squared times the resistance of the resistor, and if you remember, that is also 5 ohms. So don't need to even redo that. We get the same value, 2,880 watts. This is my true power. And the last one is the power from the capacitors, and we substitute values again. Power equals 24 squared times, and the reactance capacitance was 0.000942. And if I do that calculation, 24 squared times 0.000942, I get 0.542 watts. And this is my reactive power. So, as you can see, the true power is almost exactly the same as my apparent power. So that's a really good circuit to have. When you have the apparent power almost equal to your true power, that means there's almost no power loss. And as you can see, it's 0.542 of a watt. You're really not losing a lot of power in this circuit. But these are all the different calculations that you need to do for an RC circuit that has resistors and capacitors in the same circuit. I hope that this was helpful. If you have any more questions, remember you can write your questions and write me an email or put it in your comments. Thank you for watching.